For this lesson, we're going to look back at factoring. This will be a review of factoring patterns that you've used before, and we're going to summarize them into one chart. So our objective for this is to be able to factor trinomials and also start to factor binomials as well. So first of all, the biggest point you need to make sure you start off with when you're factoring is remember to take out the greatest common factor first. So the GCF comes out first, otherwise sometimes you'll end up not completely factoring the trinomial. So our pattern is ax squared plus bx plus c. This is a trinomial, 3 terms. And when we look at this, when a equals 1, so when we have this pattern where a would be equal to 1, that'd just be x squared plus bx plus c. It's a simplified version of these problems where you can just look for two numbers that first of all multiply to give you the c, to equal c, and that add to equal b. Okay, so we're going to look for those two numbers in this pattern. Now, just a note of caution, you can use these other techniques on this one as well. This is just the quickest way. So when we look at a problem like this, x squared minus 3x minus 10, what two numbers will first of all start off with x and x, and what two numbers multiply to get negative 10 and add together to get negative 3? Well, that would be equal to, if we look at this pattern, we'd have negative 5 and positive 2. So this would be what our factorization would equal, and it's fairly quick to get the answer for that one. All right, now let's look at what if they're a little more complicated than that. What if the a, the leading coefficient, doesn't equal 1? Well, if that's the case, if we've got a number that's not equal to 1 at the front here, what you want to do is you want to set up a pattern. This is called we'll call it the X pattern. And so to do this one, what you want to do is look at A times C, put that up in the top of this little X pattern. Down at the bottom, you just grab the B and put it down in the bottom here. And then what you're going to look for are two numbers whose product is this one, this whatever number is up here, and whose sum is equal to that one. So it's kind of the same idea here, product and sum, but it's going to be a little more complicated because you're going to have a number up in front here. So let's take a look at what this might be. So if we put an x here for this problem here, we want to set it up by taking 3 times 3, that gives me 9 right here, and then you just grab the 10 and put it down here. So now what we're looking for are two numbers that multiply to get 9 and add together to give 10. Well, if you think about those numbers, that would be 9 and 1. And so if you've got two numbers that 9 times 1 equals 9, 9 plus 1 equals 10, that's what we're looking for this. I'm going to take those two numbers and put a 9x here and a 1x here. That's going to help set up the pattern for me to do this problem. Now, the next part is where you use what's called factoring by grouping. I'm going to take this 3x squared and I'm going to split up the middle term, the 10x, into 9x and 1x. Kind of backwards on the when you're double distributing through it, so it's separating it into what that would be, and then just list the 3 at the end here. Now what you do is you go ahead and group them together. You put these two together and these two together, remembering that if there's a GCF, we're going to take it out. There's a common factor here of 3x, so I'm going to take that out. I'm left with then just an x. 3x times x is 3x squared. 3x times 3 gives me that 9x. Notice this is just x plus 3 also. If we've done our work correctly, these two are exactly the same. So we distribute the entire parentheses out. So I'm going to factor out x plus 3 as an entire factor, and then we list what's left. I'm left from this one a 3x, and you can think of this as factoring out a 1 out of this, because we can take out a 1 out of this and a 1 out of the 3. So it's left when you take out the x plus 3 and it's gone, you're still left with the 1 left over. And so this is the factorization of this trinomial based on setting up the x pattern, coming up with what your expanded look is, factoring by grouping, by distributing out the common binomial factor, and then you've got your factorization. We'll do another example of that in just a moment. Let's look at the other patterns here for this. Notice that this is a trinomial, this is a trinomial. Here's also a trinomial that can be a quicker problem if you notice I switched from x's here. If you have a squared first term and a squared last term, you can look for a pattern where these are going to be m plus n, the quantity squared. Remember, that's just m plus n times m plus n. That's what m plus n squared means. Well, what we look for here, if we got a perfect square here and a perfect square here, we look at it and say, hey, does that mean we can make this into x plus 6 and x plus 6? Can that be a quick solution to it? Notice that we do get x squared plus 6x plus 6x is 12x in the middle plus 36. So sometimes you can speed up the factorization process if you notice that the first term is a perfect square and you notice that the last term is a perfect square. It factors into the square root of that one, square root of that one, and then just the quantity squared. All right, now our last pattern. Notice if there is no middle term, there's no middle x term all by itself, it's just the squared terms. If it's two terms and there's a subtraction in the middle, look for the difference of two perfect squares. So the pattern for this would be m minus n and m plus n. Now, if you recall why that works out with no middle term is because when you multiply through, you get m squared plus mn minus mn. The middle terms will get rid of each other and then just minus mn squared. So here's an example. When we have a binomial with a minus in between and the two are squares, you make it x minus the square root of the 64, which is 8, and x plus 8. And notice that those two, when you add the 8 and the negative 8, the middle term would disappear with the negative 8x and the positive 8x. That middle term would be gone, leaving us with just a binomial that factors into this. So difference, if you see two terms with a minus in between and two perfect squares, take the square root of each and then put a minus and a plus, and you've got your factorization. All right, so those are the basic patterns for this with first examples for this. Let's go ahead and try some more examples here just to factor these and get the patterns down. So the first one here, what you want to look for is there a GCF in all the terms? Is there a number that goes into 5, 22, and 8? And the answer is no. There's no number that goes into all of those. So since the leading coefficient is not equal to 1, I'm going to use the x method here. And I'm going to multiply 5 times 8 to put up in this top part of the x. Now I'm going to go ahead and just rewrite the 22 down here. And then what I want to do is go through the factors of 40 to see what adds to get 22. Now this one's not so hard. If you think about it, factors of 40 would be 40 times 1, 20 times 2. We could also have, for instance, 10 times 4. We could also have 5 times 8. So those are all possibilities for factors of 40. Well, notice that 20 times 2 gives me that 22. So as soon as I find that one, I can stop and just say I'm going to put a 20x here. I'm going to put a 2x here. And now I'm going to rewrite it. Taking that middle term, separating the 22x into 20x and 2x, and then just writing the 8 out here. Now I'm going to group the first two together and the last two together, factor out the GCFs. So out here I'm going to take out a 5x, and then I'm left with just a 1x plus 4 when I factor that out. Here I'm going to take out a 2, I'm left with an x plus 4. Notice that that x plus 4 now is in common. I can factor that entire quantity out. That binomial comes out as the common factor. And what I'm left with is 5x plus 2. And now I've got the factorization of this. And if you were to double distribute this through, you would get this final answer. So here's a quick and nice organized way to find the factorization when that leading term is not equal to 1. Well, this one also, the leading term's not equal to 1, but if we jump too soon into the x method, we neglect to see that there's a common factor of 5. Always look for the greatest common factor first. So I'm going to take out a 5. I'm left with x squared plus, when I take out the 5, a 2x minus 3. Now, this inside part here, I could use, you can use the x method on it, using your a of 1, your c of negative 3. It would work, but there's a quicker way. Since the leading term is equal to 1, I just separate it and make it x and x, for separating out the x squared. And now, what two numbers multiply to give you negative 3 and add together to give you 2? Well, that would be a positive 3 and a negative 1. 3 times negative 1 is equal to negative 3. 3 plus negative 1 is equal to 2. So that's a quicker way to do that factorization if that leading coefficient is equal to 1. Now let's go ahead down to this one. Look for a common factor in everything. Notice 25, 30, they have a common factor of 5, but 9 doesn't share that. Now if you want a shortcut, you go ahead and look to see, hey, this is a perfect square, that's a perfect square. Let's see if this factors into 5x, and we're going to have a 3 here, and 5x and a 3 here. Now notice this could either be a plus and a plus, or notice that would not give me a negative in the middle term. We can also notice that because we could multiply negative 3 times negative 3 and get a positive 9, this actually does give me 25x squared minus 15x minus 15x gives me negative 30x, and then negative 3 times negative 3 gives me the positive 9. So this is just 5x minus 3, the quantity squared, which is quicker than doing the x method. You could do the x method on this, but 25 times 9 is a large number. To look for all the factors that would then add up to negative 3 would take a little bit of time. This is just a quicker first check to see if this possibly is the factorization. Now we look at this one again. If you jump too soon, say, hey, difference of two squares, you forget that there is a common factor. Take out the greatest common factor first. So we're going to take out the 9 and make this x squared minus 4. And then we go ahead and factor the x squared minus 4 as the difference of two squares. So x minus 2 and x plus 2 when you factor it. Notice again, difference of two squares, you could have made this 3x minus 6 and 3x plus 6. The problem is this is not the final factorization. This has a common factor of 3, so does this. You take them both out, you get the factor of 9. You'd end up here, and you might neglect to see that you've got to take out the greatest common factors. So don't start with this, start with the greatest common factor, and that will get you your final factorization quicker. Okay, so we've seen these different patterns of factoring. You want to look at the either trinomial or binomial that you're trying to factor. Look for the pattern that's listed in these 4 columns, and then once you see the pattern, use that pattern to come up with the factorization using the, if you want to, the x method if the leading coefficient is not equal to 1. If it's the difference of two squares, use that pattern. Otherwise, if the leading coefficient is 1, use the the shortcut that we have of multiplying to be the last one, adding to get this one, and also looking for the perfect square pattern as a possibility for a shortcut to factor your trinomial.